Welcome to the lesson video on LDA Visualizations. In this video, we're going to talk about a method for using the theory behind linear discriminant analysis to create a projection into lower dimensions, or a dimension reduction method based on linear discriminant analysis. So what are we going to talk about? We're going to talk about this LDA projection, which is a projection into lower dimensions that maximizes the distance between class means, but at the same time minimizes the within class spread. So it's going to give us the best way to view separation between classes, or at least linear separation between classes, when we have class labels. So let's talk a little bit about what we mean by projection and what would happen in projection in different directions. And so here I have class data, a red data set, and a red class and a green class in my data set. And I'm looking at a projection onto this line here. And so what I do is I take, for a projection, you take each point in your data set and you follow the line perpendicular to the line you're projecting on, and that tells you where that point will be after that projection. And so here's my original data, and then after projection, I have this data sitting in the line that I've projected on. So this first projection that we pick takes our two classes and projects them in a direction that's going to maybe maximize variance or come close to maximizing variance of the total data set, but it squashes the classes on top of each other, and so we don't see any class separation. That first plot is what along the lines of what PCA does. It projections in the direction of greatest variation of the total data. This plot on the right-hand side is what we're looking for. We're going to take our two data sets and we're going to project it in some direction. Same two data sets, but now we're projecting onto a different line, this line here, and we're projecting onto that line, and we see it preserves the separation between the classes. So now we could view our data in one dimension and see the separation between classes. Of course, we care more about projecting data from 100 dimensions down to 2 or 3 so we can look at them than we do about projecting things into one dimension. If our data is two-dimensional, we don't really need to project it. So here's another way to look at that class projection. So suppose I have two classes, again here red and green. Let's think about how to do this projection that maximizes the separation between my classes. So the first thought you might have is projection the direction that maximizes separation between the means. So there's the line connecting the means, and if I project onto that line, that's going to maximize the separation between the means after my projection. So that's what this would look like. This line A1 is a line that's parallel to the line between the means, and if I project onto this line, I get what I see in the picture here. My classes are now overlapping. So I've taken things in 2 dimensions where they had some separation, and I've projected them down to 1 dimension, and I've projected them in a way that doesn't give good class separation, right? My distance between my means is preserved, right? That distance, it's the same as the original distance between the means. If I project onto any other line, I'm going to have those means will be closer to each other than if I project onto this line, but I get class overlap. So what I really want to do in linear discriminant analysis projection is project in a direction that maximizes this separation between means, but also minimizes the spread of the class, right? The way I projected these classes, they have a lot of spread or variance after the projection. So this new projection A2 still keeps pretty good separation between the means, but the variance or the spread of my classes here is minimized. So that's the trade-off we're looking for. We're looking for a spread that maximizes separation between the means and minimizes the within class spread. And that's what the linear discriminant analysis projection is going to give us. And so A2 is better accounted separation because we accounted for the variance of the spread within the individual classes. One piece of notation, we're going to now go into talking about how we compute this separation, this projection that we're looking for, and we're going to need some notation. And so the projection of a point xj in the direction of a vector A, right? The vector A determines my lines, is written by this: A transpose matrix multiplied by xj. Now we're going to get into some linear algebra and some formalism with our linear algebra and some calculus and some optimization. It's not really required to know and be able to follow and reproduce all these formulas, but it's really nice to see where this stuff comes from, to see where the sort of machinery going on behind linear discriminant analysis. So we're going to kind of give a summary level. We'll see all the details, but we'll go through them kind of quickly to give a summary level understanding without taking too much time to get bogged down into the details of what's going on here. So, okay. So the goal is to find the projection onto A that maximizes the distance between the means, and we're going to normalize by some sort of variance after the projection. So to do this, we're going to need to start with formula. So the mean of class I, this is before projection, is this. So this is just obviously the formula for the mean of class I. So that's not anything new. Now we define the scatter of class I to be this. And so this formula is the same formula we've seen for the covariance of a class. It's the covariance matrix, except there's no dividing by number of samples minus 1 out front. So this scatter is just the covariance times the number of samples minus 1. So we're not divided by number of samples minus 1 to get an actual covariance. So scatter is very similar to covariance. So what are we going to do? We're going to compute the mean of each class after projection. So 2 more definitions, and these are fairly straightforward. This is a mean of class I after projection, right? This is the formula for the projection of point xj. We're going to sum up all the projected points xj and divide by 1 over n, and that gives us the mean after projection. So this little tilde on top of a letter means that's the value for that object after it's been projected. And so here we have the scatter after projection, right? It's SI with a tilde. The tilde on top means we're doing after projection. And then we just look at this formula for S, but we've projected each of the terms inside. And so these are mean and scatter before projection and mean and scatter after projection. And we need these formulas because we want to maximize the distance between means after projection, but minimize the scatter after projection. So we're going to do those at the same time. So we want to maximize the spread between those means and minimize the sum of the scatter for all our classes after projection. Right, so another way to say that is we're going to find the value for A. Remember, A is a vector. So we're going to find the vector A that maximizes the value of this, right? So we want the distance between the means to be large and the total spread to be small. So we're maximizing the ratio of distance between the means divided by the scatter. Right, so that's what we're going to try to do. That's the goal for linear discriminant analysis. We're going to find the A that maximizes this J of A. So J of A is a single variable output. So to do this, we have a little more computation, and this is fairly straightforward. These are just moving around things. This is the mean after projection, and this is the formula for the mean after projection on the previous page. And now what we say is this A transpose J, you can pull that A transpose outside the sum right here, and that's what we have written here, that A transpose is outside the sum, and then this sum is just the mean of class J, mu I, and so we have that. So this first computation says that the mean after projection is the projection of the mean. Very similar thing with the scatter. This is the scatter after projection, and you can follow through those, but we show through those series of just some linear algebra, showing that that's equal to what you get when you take A transpose times the scatter matrix times A. And so using those two, if we come down here and look at this JA, we're trying to find the value of A that maximizes this, right? That JA is equal to this formula here, using those computations that we just did, which, if we write it out a little more carefully, is this here, right? We're being a little informal, write this squared, this top here, we really mean what's written here, and then we can take these A transposes here, and here, little bit of linear algebra says we can bring them all the way out to the outside. So there's a bunch of linear algebra we're walking through here, and to the degree that you've seen this type of linear algebra before, it should make some sense. if you haven't, it's good to walk through these and see some of the stuff that goes on underneath the hood and get some familiarity with how these things are computed. So we want to maximize the value of J of A. And so here's our formula J of A. And to understand this better, we're going to make some more definitions. So we're defining the within class scatter, and that's SW. It's the sum of the scatters for those two individual classes. So within class scatter for the total data set, it's the sum of the scatters for the individual classes, and that's given by this formula here. It's a sum over all x of x minus this mu here is the mean of whatever class x is contained in, and this formula is familiar from the covariance matrix formula. And then the between class scatter, that's S subscript B for between class scatter, and it's the scatter formula but applied to the mean. So this is the mean of class I, and this is the mean of all of the means, where in this case we only have two means, so it's a little bit simpler of a situation. Okay, so what we really want to do is minimize within class scatter and maximize between class scatter. If you understand that, even if you didn't follow all the details of every formula, you understand we want to maximize the between class scatter and minimize it within class scatter. That's a good understanding of what linear discriminant analysis projection does. And so here's J of A. This is the function that we want to find the maximum value of. We want to find the A that gives us a maximum value here. So to find a maximum value, we use some calculus. So we're going to take the derivative of J of A and set that equal to 0. So the derivative of J of A, here we just put in the formula for J of A. And then this equal sign, we just use the product rule from calculus. Now we're going to multiply both sides by this piece in the bottom. Of course, it cancels that in the bottom of that formula on the left-hand side, and it multiplying by 0 by that just leaves you with a 0 on the right-hand side. Next step in our computation, we multiply both sides by this. And now this piece right here is equal to 1. And this piece right here is J of A. So we use those two pieces of information to get this formula right here. We move those around a little bit. We use the fact that J of A is a scalar, and we get to this formula. Then we multiply both sides on the left-hand side by SW inverse. And that's a matrix inverse, and we get this formula here. And so this is a generalized eigenvalue problem, and it tells us what A has to be. A has to be an eigenvector of that matrix right there, and J of A will be its eigenvalue. So this tells us the direction to project these two classes. We can solve for A if we have a two-class problem, and there's the formula for the vector A. We take the vector between the means, and then we multiply that on the left by this inverse of the scatter matrix. More generally, if we have C classes, some arbitrary number, the LDA projection will be the projection onto the C-1 eigenvectors of this matrix. So remember, PCA was the projection onto the eigenvectors of the covariance matrix. LDA is the projection onto the eigenvectors of this matrix here. And these two terms, this is the between class scatter, and this is the within class scatter. Remember, we want to, in a sense, maximize between class scatter. That's the kind of the scatter between the class means, at the same time minimizing the scatter within, or the variance within the classes after their projection. So intuitively, that should make a little bit of sense that that's the thing we want to use to compute the LDA projection. So again, just to clarify, it's really, there's a nice end result here. PCA, we project onto the eigenvectors of the covariance matrix. LDA, we project onto the eigenvectors of this scatter matrix right here. Okay, so let's go through some examples. And actually, you've seen an LDA example in the interactives and in this plot on the right-hand side that you have. So the left-hand side shows the iris data. Remember, it has 4 variables. This is the full all pairs scatter plot in R on those 4 variables with the classes colored by their class labels. And if you look over there, you can see some separation in these individual scatter plots on the left-hand side. But none of those show the full class separation. And then we do an LDA projection and we get this plot on the right-hand side. This is really a projection on LDA component 1 and LDA component 2. And you can see that we've got class separation that's a little better than even the best of the individual pairs plots on the left-hand side. So what we have is a 2-dimensional slice through the 4-dimensional space where the original data lies, and that 2-dimensional slice that we projected onto that we're showing here on the right-hand side, that projection on the LDA components, that gives you the best view of the class separation. So we've been using that in our interactives to display the 4-dimensional data in 2 dimensions in a way that we can see some approximation to how the classes are being separated with the different color regions. We've been using that because we want to visualize some amount of how the different algorithms are separating those classes. And so we need to do that in 2 dimensions. So that's why we've been using the LDA projection for that, even though until now we haven't been able to talk about it. Here's another example. This is the handwritten digits data that we've looked at from time to time. And so I think this is 9 classes with numbers 0 through 8. I don't think there's any 9s in here. And on the left-hand side, we've taken this data. It's originally in 256 dimensions. Right? Each dimension corresponds to the brightness of a pixel in the digital image taken of the handwritten digit. And out of that 256 dimensions on the left-hand side, we see PCA projected onto the first two principal components. And this was done in Python. And so here's the command in Python. It's using a custom function for doing the plot, which is provided here. But this first line does the linear discriminant analysis projection, or sorry, the PCA projection in Python. And on the right-hand side, we have the linear discriminant analysis. Again, the first line does that LDA projection. The second line makes a custom plot, and this plt.show says show that plot. And on the right-hand side, we see the LDA projection. We see much better class separation from LDA than PCA, and this is 9 classes. So to get the full benefit of the projection, we would need 8 dimensions. So we've projected really down from 256 down to 8 to see the separation between our classes. But because we can only view a projection or a plot in 2 dimensions, we're only seeing 2 of those 8 dimensions, but we still see some quite nice class separation. The 4s tend to be up here. The 0s tend to be down here. Tend to have the 3s here. The 2s are there, even though there's still quite a bit of overlap. And so on. And you can make some estimation of where the classes are. There seems to be a lot of overlap between 2 classes in this region. And then you just separate out sort of by color. There's a lot of overlap there. But you can still see, even just out of 2 of the LDA 8 dimensions, you can still see a lot of the class separation. So in review, what have we talked about? We've talked about linear discriminant analysis projection. We went through the linear algebra in some rather quick fly through of the linear algebra and the calculus involved in computing things, but what you should know is that it maximizes the between class scatter, that's separation between the means, while minimizing the within class scatter, and that's a measurement of the variance within the classes after the projection, right? That's the important thing to know about LDA projection. Why do we do this? It gives a lower dimensional projection that preserves as much of the linear class separation as possible. It can be used to view structures among the classes or to visually see how much class separation there is. It can also be used as a dimension reduction as in pre-processing, similar to PCA. And One final note, there are other methods for dimension reduction that use nonlinear methods for understanding the data and giving you dimension reduction. We're not going to go into those, but it's worth being aware of those. PCA and LDA are the most two common, where PCA preserves the variance of the data, and LDA minimizes the within-class scatter and maximizes the between-class scatter, as we've talked about. Well, thank you very much for watching.